Hey, welcome back. It's time for lesson 2 of the Sci-GaIA Winter School on Application Development for Science Gateways. I'm Bruce Becker again from the Council for Scientific and Industrial Research, San Competency Center, and I'll be taking you through the development of the Science Gateway development environment. So let's jump right in. The outline of this lecture is as follows. First of all, we want to just define what it is that we're going to be learning. Then I'm going to explain the various components of what we call the Science Gateway stack, the various pieces of software and how they fit into each other. I'm going to go a little bit into the list of tools that you need in your toolbox to be able to build an environment, either on your laptop or in some other way, to be able to use the Science Gateway stack. There's, referring to the first lesson, some hints and procedures about how to maintain a reproducible environment, because don't forget, the teachers are going to have to check what you do and make sure that we can reproduce the work that you've done to see whether it's correct or not, as well as you'll need to be able to see if you've introduced any errors or if you can do things a bit better. Then we're going to be moving on to the testing of the development environment to see whether or not your applications are going to be able to run. And we're going to have some discussion about how to implement these tests, what kind of tests you need to implement, and who should be doing these tests. Finally, we're going to talk about the practicals. The practicals will be given to you on the courseware websites, and we discuss here the things that you need to do to be able to pass the practicals. And finally, we'll tell you what to do if nothing works and you feel like you're at a bit of a loss. So let's get into it. Learning goals. What are we here to learn? So first of all, the primary goal of this lecture is for you to understand the Science Gateway stack. You're going to need to know what it is, the components of it, and why we chose them, to be able to develop your portlets. But you won't have to go very deep into the functioning of the stack. You'll see what I mean by this in a few slides. Most importantly, you need to know how they work together, and you need to know how to put them together so that you can have a functioning environment. You need to know how to put these tools to work, and so to do that, we need to see how to use those tools which we've just covered in the first lesson. That would be your GitHub repo, your GitHub account, and the corresponding Docker Hub accounts with the functionality of Docker Engine on your laptop to be able to build the environments which are going to be hosting this Science Gateway stack. This is the place where you will be testing your Science Gateway portlets, as my colleague Marco will show you in the next lecture. But let's not get ahead of ourselves just yet. Finally, you need to be able to learn how to consider and implement some tests. These tests, as you'll see, will be left up to you, and some other tests will be implemented by the school itself, which is a pretty good representation of what happens usually in the real world, where there's some individual testing and then some automated testing of whatever components get put into a code base. Right, so these are basically the 3 things that we expect you to learn from this lecture. To understand the Science Gateway stack, how to put the Science Gateway stack together, and how to implement tests based on that Science Gateway stack of your work. Right, so let's get into the Science Gateway stack and talk about the components of it. In general, in order to develop a generic Science Gateway, we need to understand the various things that are necessary in terms of underlying infrastructure. And what we mean by infrastructure is you're not going to write your own database, your own file storage, your own data transfer authentication system. All of these things are going to be provided to you by some existing library or existing piece of software which you need to plug into each other. And that's the concept of a stack. So a Science Gateway, at its heart, at the most simple expression of what a Science Gateway is just a web portal. It's a place on the web where some functionality is pulled together so that you can conduct some scientific research. But it's not any web portal. It's not like Gmail or it's not like Facebook. Those have specific targets. but the concept is pretty clear. It's a place where you go to do something specific. In the case of Gmail, send email. In the case of our science gateways, it would be do science, whatever that science is. So some infrastructure is implied. It's not just a website where you can see the information or maybe interact very simply. There's some deeper functionality. Let's go into that for a second. First of all, an application server is needed. And that application server is going to be hosting the individual applications which you will be writing. Of course, you need a runtime environment for those applications to actually execute. Now, we're not talking about the big computing environments where the HPC or grid or cloud applications will be executing. Those are what we call the back end. What we're talking about in terms of an application environment is where the science gateway applications, those things which authenticate you, which take your requests to submit jobs and actually submit the jobs, those are the things that we're talking about when we say an application environment, a runtime environment. We need a database to keep track of the various states of applications, the actions of users, and so on, because we need provenance. Your requests will be executed, as we say, on some kind of computing backend, and that backend needs to have some kind of trust relationship with the science gateway, which you're in effect hiding behind by submitting your jobs through it. So we need to have a way to keep track of who's doing what and what effect that is having both on the science gateway and on the applications on the computing backend. So a database is needed. Finally, we need some kind of library to translate our actions on the web to actions on the computing infrastructure. So when I click a form that says submit, that has to be translated into please submit a job to me on this particular site in this particular way. And of course, we want to be able to do that to as many computing infrastructures as possible. As we saw in the inaugural lecture by Roberto, there are many of these, and they tend to have slightly different interfaces. So, in each of these components of the stack, we have several choices available to us. And if you were starting from scratch and you wanted to build your own science gateway, you would have quite an array of things to choose from. In terms of the application server, for example, you may be a Python developer, so you'd like to choose a Python stack. That would be something like Django with a Python execution environment behind that. Similarly, you may want to write your applications in Ruby with Ruby on Rails, and so on. All the rage these days is to write applications in Java and JavaScript and to have them hosted in a Node.js environment. All of these things may be very popular on the web, but we'll see that when it comes to writing science gateways, a different choice was probably going to be the better one at this point in time. I'll leave a little parenthesis there to say that these things are evolving quite quickly, so by the next time you see these lectures, the situation might have changed. So that's for the application server and for the runtime environments. Remember that specialized library we mentioned just before that took your actions on the web and translated them into actions on the remote distributed computing infrastructure. Well, that library needs to understand how to take the action, in this case, for example, submit a job, in every language or execution environment that you need to support. So you could do that for every language or do it specifically for the language in which your stack is written. Or you could choose a different philosophy which says that you can have a standard API which whatever language that your portal is built in can call based on its particular implementation, and then have that translated uniquely to the computing backend, so that you only write your code once. And that means that you don't have to re-implement the connectors between your science gateway and whatever different kind of computing backend or data backend you have. In fact, such a thing does exist. It's called Sci-GaIA, and that stands for the Simple API to Grid Applications. This is a standard of the Open Grid Foundation, and it has several implementations. So what you'd want to do next is check whether your favorite language has an implementation of Sci-GaIA. So that's the specialized library. Let's move on to the aspect of a database. So there are many different kinds of storing persistently data which has to do with web applications. You may want to go with the traditional LAMP stack, in which case you would choose a MySQL database, or you may want to go with a slightly more advanced database, maybe a Postgres database, etc. You may even want to go with no SQL database, which may be fast in some cases. But in any case, you're going to be needing a way to store the interactions between the user and the Science Gateway, as well as the Science Gateway and the computing backend. Right, so what you need to know then is that you need to ask yourself, does the database that you like, that you choose, does that have the correct schema which the relying infrastructures, those places which we're going to be submitting jobs to, does it have the correct schema to be able to track the right actions in the right way for the right amount of time, etc., so that you can obey their user agreements. So this is a discussion about the various components of the Science Gateway stack, and I've tried to be as general as possible in the first few slides to show you that there are many options available, and what we're going to be going through now is the specific selection of components for the Catania Science Gateway framework. The reason we're choosing this is not just got to do with the fact that we are part of the consortium running this school. It comes from a long historical experience in developing science gateways for general purpose computing infrastructures. Right, so what we've chosen essentially for the various components is as follows. In terms of the execution environment or the application server, we've chosen a Java stack. So that Java stack translates into a runtime environment and a Java development kit. One level up, in terms of the application server, we're talking about the Glassfish application server. Then, in terms of the website, the portal builder, we've chosen to use the LifeRay portal system and its software development kit. Just beneath that, we have what we called before the specialized library, the way in which we translate the actions taken on the portal to actions to be conducted on the computing infrastructure. And as we mentioned, there is a standard API to this functionality. Since our stack is a Java stack, we're going to be choosing the Sci-GaIA implementation. And then finally, as a database, we're choosing MySQL. This is probably the least interesting choice, because almost any database could play the right role here. The only reason that we're going with MySQL is because of its ubiquity and of the fact that we already have an implementation of the correct configuration of a Science Gateway database in MySQL. If you're feeling very adventurous, as a comment and aside, you may want to see whether or not you can implement the same database in a different kind of stack. Right, so let's move on. I'm going to say one or two words about each component and our choice, why we made that choice, why we maybe think it's a good or a bad choice, and just leave some room for discussion, which we invite you to undertake on, of course, the discussion forum. That's discourse.scigaia.eu. Starting with the Java components. So at the very bottom layer, we've got the Java runtime environment and the Java development kit. Now, the Java community process, which we see here on the slide, is a rigorous way of getting new standards approved by a very wide community of developers, which are the Java enterprise developers. And so it turns out that the specification of how to represent and how to make a portlet, a piece of functionality in a website work has been very mature in the Java community. In fact, they've got two so-called Java specification requests, which are essentially Java community standards, which define how a portlet should be built and how it should work. And those are JSR 168 and JSR 286, the so-called portlet specification. So any website or any portal container respecting those standards will be able to execute your portlets, which gives you a wide range of portability options. You can put your portlets into lots of different application containers, and you can move it between science gateways, which is a major benefit if you want to consider things like scaling or community collaboration and so on. Let's say a few words about the application server. So again, we've chosen the Glassfish application server, but there are many available options. So you could have chosen any one of the very good open source Java application servers, or indeed a commercial one if you have that available. In fact, there's hardly any very good reason to have chosen Glassfish. There's no particular functionality of Glassfish that either Liferay or our portlets will be using, but we are referring to Glassfish in these lectures as the kind of de facto standard. So there has been some experimentation, to my knowledge, of people trying to implement the Science Gateway stack with Tomcats. One more level up the stack, and we're now at the level of the Science Gateway portal container. So this is an application of the Java application server, and it's the container in which we will be putting our application portlets. And that is the code or the work that we as students, or you as students, will have to do. As mentioned, we've chosen Liferay. There are not that many very good open source and mature application containers out there. Liferay is one of the most mature and indeed has many good aspects of functionality. Not just the Liferay portal, but there are aspects of the social office which have implemented Liferay Sync for document sharing and so on. So I invite you to have a look at this, the features of Liferay on their website. Since we've chosen the Java stack, indeed we can put our applications, our portlets, into any kind of portlet container, any kind of application container. The chances are that your application will be able to deploy and work. However, as development of the stack has continued, we've started to make more and more use of deeper functionality within Liferay by the portlets themselves. And this brings a little bit of better user experience and tight integration with the functionality of this portal itself. Right. So why do we need to use a portal at all? Some people may consider the fact that it's over heavy, maybe a bit bloated, you don't need all of that functionality. Why not just start with a bare bones CMS and include some applications within that? Well, indeed, the Science Gateway is quite different from a content management system or a simple website. There's lots of internal business logic which needs to be done, and various roles to be taken by the Science Gateway application manager or simple users and so on. So it makes more of a sense to use something more like a portal and less like a CMS in this case. Coming back to the more specific aspects of our Science Gateway, which depart a little bit from the generic web development and go more towards the science part of the Science Gateway development, we come to that specialized library I was referring to before, and that is the J-Saga implementation of the simple API to grid applications. This is the library which allows us to receive calls from the Science Gateway and submit those calls, translating them appropriately to lots of different kinds of target infrastructures. These can be distributed computing infrastructures like production grids. They can be single cloud sites or distributed cloud sites in the case of the federated cloud of EGI. Or they can even be single HPC centers with direct access via SSH. So that provides us with a very powerful way to provide access to our users through one application. We don't have to write various pieces of code to access this kind of infrastructure or this site or different sites. We can just write that piece of application which says submit job, as you will see later on when Mario Torrisi gives his presentation, his lecture. You can just write the piece of code that says submit job, and J-Saga will translate that into whatever the target infrastructure needs. So that's very powerful, and it allows you to kind of abstract away all of the technical details of the computing infrastructure. And those can be quite deep. You need to have some kind of authentication and authorization. The portal needs to discover resources. You need to be able to do quite complicated job submission and management. There can be simple job submission, parallel job submission, workflows. And the same goes for data, extracting data, storing data, discovering data. So without using a portal and without using the Sci-GaIA API, you would have to write all of this functionality for every use case yourself. And that would be quite limiting in the general case. So finally, we come to the last piece of the Science Gateway stack, and that is the so-called grid engine. Although this is somewhat a misnomer at this point, because the concept of a computing infrastructure has been abstracted by the Sci-GaIA API as well as the actual grid engine. So we're just using grid as a kind of catch-all term for anywhere you can submit a job. And that can be a cloud interface, a HPC interface, or an actual distributed computing interface, which may look like Globus or G-Lite. Right, so what the grid engine allows you to do is to access certain functionality which is going to be typical of a community science portal. What I mean by community science portal is that place where your team or your community goes to conduct their science, to submit their jobs, to retrieve their data, and to interact in general with the distributed computing infrastructure on the back end. So that provides you with functionality like, in this case, submitting complicated workflows, monitoring the status of jobs, making sure that the jobs go to the correct infrastructure, and so on. Now, putting it all together, we can see that various aspects of the stack can be grouped more logically than others. In particular, the database itself can live alone, and all of the other aspects, the Glassfish application container, the runtime environment, the various libraries necessary to interact with the grid, and LifeRay itself, those have more kind of a web scope because they face the internet. So we can start to see how to build two separate containers in Docker, one to host the database and another to host those things which will provide web functionality. So before we move on to actual portlets, which is the reason you're attending the school, let's just take a step back and see what we've got in our toolbox to be able to build these containers and make sure that we've built them correctly. These three layers can be quite complicated, and so what we'd like to do in this lesson and in the practicals that follow is give you the tasks that are necessary to ensure that you have a working development environment. And by a development environment, we mean an integrated database and web stack, which allows you to develop your portlets. We've talked about the learning outcomes. We've decided what we need to learn as the students. And we've just covered the components of what we call the Science Gateway stack. Those generic components which you need to build something that's going to be a Science Gateway. And we spoke a little bit about our individual choices for the purposes of this course and the reasoning behind them. But how do you build the environment which contains that stack? It may be easy to do once off, or maybe not so easy, depending on your skill level. But what you want to be able to do is to ensure that you've got the stack in a reproducible, always available way. And to do that, we're going to need some tools in our toolbox. So let's have a look what's in our toolbox. First of all, we need to ask ourselves two questions, and I'm going to give you the answers to them. There may be many different answers, but these are the answers that we will consider correct for the purposes of this course. So the first question is, how can we build a reproducible environment to test our work? And how can we make sure that this environment is the same environment that the others, be they our team members or our teachers, how can we make sure that that's the same environment that they are using to validate our work? All right. So you can immediately see that it's going to be very difficult to do everything directly on your personal machine or laptop because only you have access to that. And so the answer is, well, it's obvious, man. We went into this in the first lesson. It's just Docker containers. That's the easiest way to provide a validated, checked, consistent way of distributing an environment. And so we'll be using Docker containers to create the development environment which you'll be working with. Second question is, okay, so now that we know that we have to use Docker containers or some kind of container, what's the best way of expressing that? If you think back to lesson 1, there were a couple of kind of dogmas, dictates that we said were very important. And one of them is that even if you've done something correctly, if it's not expressed in a persistent way, in a change-controlled way, it doesn't exist. And so you need to keep track of how your actual environment evolves, make sure that you're on the right path, and maybe roll back if you make a mistake. And so the answer to that question is, well, you should express your environment in something that's text-based so that you can keep control over that. And in the case of Docker, the most obvious way to do that is with a Docker file. Okay, so at the bottom of the slide, you see the kind of link between the repository in which you keep your Docker file, which is change-controlled, maybe in GitHub, the actual file, which is changing from commit to commit as you go down, and the actual environment represented there by the nice little Docker whale. Every time you change that Docker file and you make a git commit, the Docker environment, the image that is built by that file, also changes. And these can be tested by Jenkins or any other kind of testing service. Right, so let's get into how we're going to be using those two tools in our toolbox, Git and GitHub and Docker Hub, how we're going to be using those to build our development stack. First, a word about processes and containers. So if you read diligently the Docker website, the documentation, it says that good practice is to keep only one process in a container. However, we've got two processes because we've got one database and we've got another set of things which are providing our web stack. In fact, we've got a Java process, a Java server, which is running an application called Liferay. And so we need to separate these two things into two different containers. And so we can kind of think of one of them as being the database container. Everything database related is going to go into that container. And the other one is kind of the web container where all of the external traffic comes from and where all of the web things happen. And so they clearly have different roles. One is for storing data and serving data to and the web container is for interacting with users and for storing in various interactions between the users, the Science Gateway, and distributed computing infrastructure. For example, the database doesn't have to see the internet. This should not be contacted by the outside world. So how do we make sure that these two containers are properly linked together, are generated in a coherent and consistent way? Well, actually, Docker provides you with the means to do that, and they call it Docker Compose. So that's another text-based way, in this case using the YAML language, that stands for yet another markup language, and the web container, and how to properly link them together, and how to test that you've done everything correctly. So we're doing this in a particular way, step by step, just to make sure, since we are at a distance, that you know what you're doing, first of all, so we can check every step in the process, both at the level of the Docker file, so on a text base, as well as at the kind of binary base. We can see the image that has been created and go inside and check whether or not you have made the right environment. So let's get our hands dirty and get started with what to do. I'm going to describe a series of tasks, and at the end of the lecture, you will be able to go to the courseware and conduct these tasks and submit them as your assignments. So basically, we have 3 steps. Well, 4 if you count the getting started before you go crazy step. The 3 steps involve building the web image, and then building the database image, and then linking them together with Docker Compose and our app.yaml file, which describes their relationships. But before you go crazy, you just need to get started on the right foot. And that means doing some very simple house cleaning. Essentially making sure that you've got all of the right tools at your disposal. So I know you've done this before in lesson 1, but it doesn't hurt to do it again. Check that you have access to your GitHub accounts. Check that you can create a repository on the web as a remote for holding the code that you will write in these assignments. Check that you have access to your Docker Hub account, both via the web as well as via the command line, so that you can pull and push images. Make sure that you've got a fancy editor, the one that you like. And it may be worthwhile at this point to take a little bit of time and see which automation tools are available to you. I'll leave that as kind of an exercise for the keen students. So once you've done that, you can start getting to work. You're going to need some directory to work in. Just to kind of, I'm going to be referring to this as your work directory. It can be whatever you want. Some place where will be the top of a directory structure which things will live underneath. Because we're going to be downloading some software, it's going to live relative to this directory, and so you need to have that. No matter what it is, just make sure that you've got that and that you know where it is. So once you've done that, you can go into that directory and start editing files. So once you edit files, we want to make sure that you do that in a clean Git directory. So the first thing you do is git init. Second thing you want to do is make sure that you can push those files to your GitHub remote, and that the GitHub remote is linked to your Docker Hub so that you can have an automated build. This automated build will be one of the ways in which you test whether your work is correct, because if a build fails, you'll know automatically from Docker Hub. Now remember that these are assignments, and the staff lecturers, we're going to be having to check what you're doing. We can only see the end result of what you do. So I want to spend a little bit of time talking about a suggested workflow or suggested workflows which you may want to go through. Now remember, you're free to do whatever you want, but we have to evaluate you on the results of your work. We can't see any of the intermediate steps unless it's been kept in change control. So here is the kind of suggested workflow for a more or less professional developer to undertake. Try to do as little as possible yourself. That is, the only thing you should really be doing is writing code. If you're a developer, that's what you do. You write code. The things which are necessary to check and make sure that that code is quality code are done by other things, mostly automation. And so your workflow should be something like editing a file until you think that it's correct, then committing that change to Git and pushing the change to GitHub. And that's all. Then you will see, as you see in the picture on the bottom, the file is edited, a commit goes into the repository that automatically builds an image on Docker Hub, and we will be able to see both the code in your GitHub account as well as the image directly linked to that specific change in Docker Hub. And so we'll be able to very easily verify what it is that you did, whether or not it's correct. So we suggest that you follow this kind of workflow as close as possible. In fact, it's very, very simple. On the downside, this doesn't give you much control over making mistakes. So it's very easy to introduce mistakes, at least in the beginning, and you're a little bit blind without doing things locally to know, if I'm writing this piece of code, what is the effect going to be? In a sense, you don't really matter, because all of these things are automated, and one commit is worth 1,000, although that becomes a little bit difficult to keep track of what's been done. So let's look at a more realistic workflow, which you may want to follow in the beginning. That's kind of a semi-automatic workflow. We still have the automated build of the Docker image, but in this case, we have a little bit of manual checking on your part before you make that Git commit or before you commit the Docker image to Docker Hub. So in this case, you would be editing your Docker file, and before you commit that, you want to see what it does. So you try a Docker build, and then you want to go and see functionally, is this image correct? You would do a Docker run, and that would create a container for you to enter and see if things are correct. So you can see why a certain file is not present, maybe the version of some piece of software is incorrect, and so on. And this will create, as you see, those containers, the images actually, which we can't see. Those are invisible to the staff, but you have them on your private laptop. Once you've guaranteed yourself that you think that piece of work that you've done is correct, and you can now commit the code, you do what you did before, git commit, git push, and that will build on Docker Hub the image which you think is correct. So we can still compare a piece of code with an image and evaluate you on that, and we won't be able to see all of the bad things that you did before. So this might be a good way to get you started and give you a little bit of confidence, but it does slow you down a little bit, and it's very opaque to the lecturer. So if you do get into serious problems, we can't see what you've done, and so we can't help you. Before we get started on the actual tasks, the final word on testing. So remember the lecture, the first lecture, we touched on the aspects of continuous integration. So one of the things you want to be sure of is that the work that you do is going in some positive direction, and that you're not failing or making huge errors or mistakes. So to do this, you need to test the work that you do, and you need to test it against something that you think should be correct. This can be done in two ways. This can be done either by having kind of sanity checks to see whether basic things are there. Can I actually build this container? For example, would be a sanity check. If the Docker Hub build fails, if it's automated, then it's an insane build because it didn't build properly, and so that's one automated check. But you can have slightly more detailed functional checks to say something like, I expect this container to be able to do the following action. For example, edit a file or create a user. And if you can't do that, then your test has failed. So you may want to think about adding some kind of script or post action into your Docker file to execute these tests. This is something just to keep in the back of your mind for the future. Right, so let's go into the first of those three steps. In fact, I've broken this up into a couple of sub-steps. Because we're talking now about that web container, thing that has the Java application server, the runtime environment, the liferay application, and all of the various dependencies of the grid engine in that. So that's quite a complex thing to build. So the first step that you have to do is just to build the Java environment. And so what you see on this slide is the very minimal snippets of a Docker file to get started. And what we want to see here is that you need to start from an existing image, which you think is probably the correct one. In this case, we've shown you that we're starting here from Ubuntu Trusty. You can also choose a much smaller Linux distribution like Alpine, or you can go for an RPM-based distribution. This is one of the assignments to do, so we're leaving this explicitly vague on which base distribution to choose from. So please feel free to explore and experiment. Here's an example of how to go about adding Oracle Java 7 to this image. So we're using the Dockerfile syntax here. You can go and see the full reference of that on the web. And what this does is just to configure the installation in batch mode of a Oracle Java installation. Okay. So that would be the second step of the assignments. The third step of the assignments is to ensure that you've got the Glassfish application container and the liferay application in your container. So here I haven't given you any Dockerfile snippets because we want you to translate this English into the code that you submit as your assignment. And the steps are essentially as follows. First of all, you need to download the liferay application. And I've given you the links here where to get that from. Second of all, you need to ensure that the necessary changes are made to the environment and that you update the Glassfish admin password to whatever it is that you want it to set to. Finally, before exiting the container, you need to ensure that the Glassfish domain for Liferay has been started. To check, so we will be checking that the 3 or 4 network ports necessary to check this container have been properly set. The first one is 4848 for the Glassfish admin access, and then of course the HTTP listeners on 8080 and 8081 or whichever ones else you configure. The fourth and final step of creating the web container is to make sure that those specialized libraries that we referred to before, the grid engine, that's available in your container so that you can have access to them in your portlet. So to do this, again, we haven't written explicitly what to do in the Docker file, and we've left it up to you as an assignment to implement this in the next phase of your Docker file. So what you have to do is to download the grid engine jars, the libraries, from the URLs which you see in the slides, and they will be on the courseware as well. Ensure that they're in the proper path. So what we've got here is kind of a symbolic reference, path to Liferay portal. Wherever you've downloaded the Liferay portal, relative to that, there is a subdirectory called domains/domain1, and then a subdirectory called lib. And the dependencies have to be put into that subdirectory in your Docker file. So once you've done that, one of the tests that you implement can, for example, to be check that the number of jars in there is correct and that certain jars, the jar files, are actually present. Just wanted to mention that since you're building a container, please, it should be as small as possible. So any temporary files you may have downloaded, for example, the zip files or copies of files, be sure to clean them before committing that container. You can do that either by hand or in the Docker file itself. Right, that was how to build the web container. Let's move on to the database container. In fact, the database container is so simple that you can choose an existing container from Docker Hub and use it almost as is. The only thing you need to check is that it has the proper communication between itself and the outside world, in the sense that you should allow access to the MySQL database daemon on the correct port. And of course, the MySQL database service has to be started when the container starts. Step 3, as we said, was putting it all together in this combined environment, and we're going to be using Docker Compose to do that. I've showed you again the kind of symbolic representation of these two containers and the components of the Science Gateway stack that they contain. So your assignment for this part will be to install Docker Compose as described in the link in the slides, and then write the very small app.yaml, which will describe the relationship between your DB container, your database container, and everything inside the web container. So once you've done that and you've committed it to your repository, we can check it, and we can also check the results of this piece of code that you've written. So that's how to build the development environment. Now let's move a little bit on into how to test. So well done. If you've done everything correctly, then you've got a working software environment in a container, in 2 containers actually, which is going to allow you to very easily reproduce the development of your portlets, both on your laptop or with your colleagues or even by us. So the question you should ask yourself is, does this thing actually work? You may want to kind of test it manually, but we won't be able to test it in the same way that you do. And so you should provide a means as well as the metrics for testing your containers. And what we mean by that is that you should provide some way for executing the tests that may be internal to the piece of software that you've written, in this case your app.yaml or your 2 Docker files. And the metrics should be what you consider as good. So how many files are in a particular directory, you should specify what the correct number is, and so on. Again, we've left this intentionally vague because we want you to think about how this environment should actually be working properly. Okay? There is no particular correct answer, but there are some generic good answers. Right. So, for example, where do you think that these checks should be implemented? Should they be implemented directly inside the Docker file when you build the image? Should they be implemented by yourself typing something on the keyboard? Should they be done in some automated way from your laptop or by some service hosted somewhere else? As you can probably tell from the tone of my voice, the last one is the best one. So here's how most of the testing will probably work. What you want to see everywhere is a big green button or big green badge that says build parsing. Because by putting that into the README of your project, you will be showing whoever is reading the project that you are actually serious about your project and you've tested it and those tests are passing. That's even more convincing if you have different kinds of testing platforms. And so the tests that you provide as internal functional tests are very important, but independent, unbiased tests, which will be done on the part of the school in our infrastructure by Jenkins, those will verify other aspects which you may not have considered. Those will, for example, check whether or not you will have some give me a second, I'm looking for a word. Some negative effects on the target infrastructure. You may not know what the target infrastructure can or cannot do, and so we are the only ones who can implement that test. As a good rule, though, you should try to use as many different testing platforms as possible. And if you look at the link I show here from GitHub/integrations, you can see a couple of selections which are very easy to get up and running with. And I'm just showing you two here. One is Travis, very widely used. The other one is Circle-CI, another hosted continuous integration platform, which also has the option of deployments and testing throughout that pipeline. They all test slightly different aspects in slightly different environments, and so by doing that, you're kind of improving the quality and health of your code, as well as giving a much better impression to newcomers or reviewers of people who may see this in GitHub or who may even want to hire you later on down the line. So, on to the last piece of this lecture, and that is the practicals. So we assume that you've done all of the hands-on about setting up this environment. Now and you've implemented one or two tests to check whether or not the environment is correct. Now we're going to be leading into the third lecture, which will be done by Marco Fargetta, on how to develop portlets. So to do that, you're going to be needing what's called a software development kit for Liferay to be able to build these portlets. There's two pieces of software which you'll need on your laptop, and those are the Liferay bundle, which is the same Liferay bundle as you put into the web container. You're going to need that for simple functionality reasons on your laptop. Excuse me. And you're going to be needing the Liferay software development kit, which is a set of scripts and plugins which Liferay offers as a way to make it easier to develop portlets on your development machine. So note that we're separating now the two kinds of environments. You've got the environment in which you'd write code and develop your portlets with your IDE, which may be NetBeans or Eclipse or whatever other editor you like. And then there's the so-called development environment, which we've just been building in containers. And that can also be on your laptop, but you need to be able to verify your work with other people, and so distribute that environment as is with the work that you've done to other people, as well as testing environments. And so that's why we've gone to all of this effort to make a reproducible development environment that looks just like the one that you've got on your laptop. So the only thing you need to do in this practical is to ensure that you've properly linked the development environment in your container to the environment in which you're writing code on your laptop. And that essentially means running the container, exposing the correct volume, which hosts the plugins of Liferay, the software development kit of Liferay. So that means that, again, we're being explicitly vague about how to do this. But in the Docker file, when you start the container containing the development environment, you need to mount the directory that sits under the path to your SDK/dist to the path to liferay/deploy on the container. So once you learn how to do that, whenever you write code in your sort of development environment on your laptop and you try to build it, it will start an automatic build in the development environment on the container, and that will be it will be possible for us to evaluate and verify that as well by committing the container itself. Okay, well done. You kind of made it through lesson 2. That was a hard one. You're going to be moving now into lesson 3, which will be given by my colleague Marco Fargetta. He's going to tell you much more about how to write portlets. So I hope you're looking forward to that. Before I leave you though, I wanted to tell you what to do when you get stuck, because you will get stuck, because everybody gets stuck. You and I get stuck all the time. You know what to do. If you have any issues, open a topic on the forum and we will discuss it in public over there. In fact, this is how LifeRay became such a widely used platform, is that people were discussing it all over the place. I'd also like to just mention again that we have explicitly left many things unclear or vague. And that's because we want you to think about the question and try to implement your own solution. You will be evaluated not on necessarily the originality, but whether or not your solution works, okay? So it has to be verifiable. It can't be something magic that you just say, well, I did something like this. It has to be verifiable, and that means that we need a piece of code directly linked to a Docker image. Don't be discouraged if you get errors or if you see problems or if you don't know what's going on. As soon as that happens, maybe after the first or second attempt and you see something's not working properly, contact a colleague, contact a teammate, open a topic on the forum. Don't waste any time on that, because probably if it's something that you're experiencing, the other students will also be experiencing it, and so you can share your experience, or someone may have solved this problem. But there's also a third case, and that's we may have made a mistake. So if we have made a mistake and we've tried hard not to, please let us know. We'll be very honest about fixing mistakes and making sure that you get credit for finding bugs. As you go through these lessons, make sure that you keep the various documentation handy. The Docker Engine user guide is going to be a good one, as well as the Docker Compose user guide. And you may also want to have access to the YAML reference card. Those 3 things are the final 3 links which you find in this presentation. So, thank you very much, and I'll hand you over to Marco Fargetta.